In this video, I'm going to demonstrate how to use a regression-based approach to answer questions that are typically addressed using a one-sample t-test. So here we have a data set that has indicators of 5 different personality traits, the big 5, and they are all measured on 1 to 5 scales with higher numbers indicating more of that variable. So first I'm going to demonstrate how to run the analyses kind of the more traditional way in the one sample t-test, and then I'll demonstrate it in regression. So I'm going to do this twice. So let's focus on the extroversion variable here. Oh, and I should say I'm going to be demonstrating this in Jamovi here. And I'll make this data set available to you in the description box below. And Jamovi is free to download. I'll put a link to that in the description also. So we're going to run a one sample t-test. So as I said, these were measured on scales ranging from 1 to 5. So we are first going to run a one sample t-test comparing whether the mean of the extroversion is significantly different from 0. This is not very useful, but I'm going to demonstrate it first, and then later we'll run a more useful test. So to run a one sample t-test in Jamovi, you go up to t-tests, you click one sample t-test, you bring over the variable of interest, so in this case we're going to use extroversion. Okay, we're going to leave the test value as 0, so what this is now doing is comparing whether the mean of extroversion is significantly different from 0. Well, I'm also going to ask for the mean difference, and let's just go with the mean difference for now, and the descriptives. So what we can see here is that the mean for extroversion is 3.487, and this value is significantly different and significantly greater than 0. I know that because the p-value is quite small. The mean difference here is really the mean of the variable minus whatever your test value is. In this case, it's 0. So it's not surprising that the mean difference is just the mean, because the mean minus 0 is just the mean. So again, this isn't very useful, but I'm going to use this as a jumping off point. So I'm now going to run this in a regression-based approach, and I'm going to use the Jamovi module linear models. This doesn't come with Jamovi by default. You need to go over to modules and then add it from the Jamovi library. So I've already done that, so I'm going to go ahead and use this, and I'm going to use the general linear model function specifically. Okay, and then watch what happens in Jamovi. Well, let me just actually grab one more thing. So I'm going to go down to options and ask for additional information on the intercept, because this is essentially, in a regression-based approach, what we're doing here is we are testing what's known as a simple model, or a model that has no predictors in it, and therefore what we're testing then is the intercept. Okay, so let's look at the output that Jamovi gives us. A lot of this is kind of blank. Jamovi in this general linear model generally is expecting predictors, and we're not giving it predictors. We just have an outcome variable. So this kind of looks weird that it's blank, but if you go down to the parameter estimates box, it does give us a test. And we have a p-value. So what is that testing? Well, let's take a look. So does any of this information look familiar? So this 3.487 should look familiar, because that was the mean that we got from the one sample t-test. So 3.478, okay? That's exactly what Jamovi generates as the intercept in this model. So the mean is the single value that will reduce error the most, therefore that's the estimate. And then if you look at the t-value associated with this test, you could also look at the degrees of freedom and the p-value. These will match perfectly with the results from this one sample t-test. Degrees of freedom 499, the test statistic of 219.618, identical, and then the p-value of less than 0.001, identical. And I asked for this a little late, but the 95% confidence interval around the mean difference, I believe it should match perfectly. Yes, so it matches perfectly with this 95% confidence interval around the estimate of the intercept. Okay, so again, this estimate of the intercept is, this is actually just the mean of the outcome variable. Okay, so as I mentioned before, the testing it against 0 is not very useful given that the response scale of the variables of interest were measured on a 1 to 5 scale. So this is asking if that mean is significantly different from 0. That's not very useful. A much more useful value would be testing whether or not the value is significantly different from, let's say, 3, the midpoint of the scale. So let's run that the traditional one sample t-test way again. But this time, so again, extroversion, let's bring it over. This time, let's change the test value to 3. And let's again ask for the mean difference, the confidence interval around that mean difference, and descriptives. So the descriptives shouldn't be any different, right? So the dependent variables, the same. So the mean is still 3.487. Okay, that matches what we did last time. But what you should see here is that the test statistic is now different. It's no longer like 219. It's now 30. That's because now what Jamovi is testing here is whether the 3.487 is significantly different from 3. That's a value much closer. So the test value is much smaller. Okay, and you could see now that the mean difference is 0.487. So that shouldn't be that surprising because the mean of 3.487 is this much different than 3. Okay, so now we are going to run this in a regression-based approach. So there's one step that you need to do first to do this in regression. So to do this, you need to create a new variable. And essentially what you need to do is we're going to use the new computed variable. So all I did is I clicked here in this blank cell, and then it shows this these buttons. I'm going to click New Computed Variable. So then I'm going to give this a name. So let's say extroversion. And then what we're going to do here is we're just going to deviate it from whatever test value we want. So we used a test value of 3 last time. So we're going to deviate this from 3. And so to do this, I'm going to click this function box. This gives me a list of the variables. I could double click extroversion. So that brings it up. And we're just going to subtract 3 from everybody's score in extroversion. So here's my new variable. So there it is. So once we have this variable, we can essentially go back and run the same tests we did before in this general linear models function. But instead of bringing over the normal or the original, I should say, extroversion variable into the dependent variables box, we're going to bring over the deviated 3 version. Okay, so when we bring that over, I'm going to ask for additional information on the intercept because this is an intercept test. Things should start looking familiar again. So what's the estimate here? Now the estimate is the mean difference. So really you could think of this estimate as the mean difference. So if you remember from what the model is doing is testing, is this mean difference significantly different from 0? Which is a slightly different way to word the exact same question that's being tested here. So what you can see is that the degrees of freedom is identical, the t-value is identical, and the p-value is identical. And why I asked for the additional information on the intercept here is it gives you this row of information. And this just gives you an f test, which is really, if you just square this t, it gives you this f. But it also gives you this value, this partial eta squared, which if you're using a model comparison approach from the Judd and McClelland data analysis book, this would represent your or your proportional reduction in error. Okay, so that is how you run one sample t-tests in regression.